When the Mississippi split, scientists thought it was a glitch in their instruments, until they saw the footage. The Mississippi River, a lifeline stretching over 2,300 miles, has just made headlines for all the wrong reasons. A sudden geological shift has split part of the riverbed wide open, leaving experts scrambling for answers. Some call it erosion. Others suspect something much deeper. Whatever it is, one thing's clear: this is not normal. Don't miss what experts found after the split. It's not what anyone expected. The discovery that shocked scientists. Back in 2021, coastal geologist Alex Coker was doing what many of us did during the pandemic, scrolling through satellite imagery online. But unlike our casual browsing, his discovery would reveal something truly astonishing. Coker, who works at the Louisiana University's Marine Consortium, noticed a dramatic change in the Mississippi River Delta that made him do a double take. Where there had once been a tiny crevasse barely wide enough for a small boat, there was now a massive waterway pouring an incredible amount of water into Quarantine Bay. The channel, which scientists now call Neptune Pass, had transformed from a narrow crack about 30 to 50 meters wide into a roaring distributary averaging 200 meters across. In some places near its mouth, the channel had grown even wider. The depth measurements were equally shocking. What had been a shallow cut just 3 to 6 meters deep in 2016 now plunged to depths of 30 meters in certain spots. This wasn't a gradual change that took decades or centuries. This dramatic transformation happened in just a few short years, primarily between 2019 and 2021. When Coker and his research team calculated the flow rate through Neptune Pass, the numbers left them stunned. The channel was diverting approximately 118,000 cubic feet of water per second from the Mississippi River. To put that in perspective, that's 5 times greater than the discharge of the Hudson River flowing into New York Harbor. During periods of high flow, the Neptune Pass carries about 15 to 17% of the entire Mississippi River's water volume. By discharge alone, Neptune Pass would rank as one of the 10 largest rivers in North America and approximately the 100th largest river on Earth. Neptune Pass represents something profound, a rare glimpse into how rivers naturally behave when they're allowed to follow their instincts. For nearly a century, engineers have controlled and constrained the Mississippi River with an extensive network of levees, dams, and flood control structures. Neptune Pass formed in one of the few areas along the lower Mississippi where the eastern bank lacks significant human settlement and remains relatively untouched by engineering projects. Here, the river found an opportunity to do what rivers have done for millions of years: find the easiest path to the sea. The historic 2019 floods that changed everything. To understand how the Neptune Pass came to be, we need to rewind to 2019 and talk about one of the most significant flood events in recent Mississippi River history. That year, the Mississippi River experienced exceptionally high flows due to record-setting precipitation across its massive drainage basin. The river stayed above flood stage for more than 235 consecutive days, placing extraordinary pressure on its banks throughout Louisiana. Before 2019, what would become Neptune Pass existed as a small feature called Proto-Neptune Pass, with historical surveys from 2016 measuring its flow at only about 300 cubic meters per second during high water. It was essentially a minor outlet that local boat captains could barely navigate through in a 24-foot bay boat. Nobody paid much attention to this unremarkable feature because the Mississippi Delta has dozens of similar small crevasses and cuts along its lower reaches. Then came the relentless floods of 2019. As billions of cubic feet of water surged down the Mississippi hour after hour, day after day, month after month, the river began probing for weaknesses. In the area across from the fishing town of Burris, Louisiana, about 70 river miles south of New Orleans, the river found what it was looking for. The eastern bank in this location wasn't reinforced with the massive levees that line most of the lower Mississippi. Without these barriers, the relentless water pressure exploited natural vulnerabilities in the bank's structure, and the transformation began rapidly. Satellite imagery from February 2019 shows Proto-Neptune Pass as a thin line, but by March 2021, that same location revealed a wide, powerful channel cutting through the landscape. What makes this event particularly significant is its rarity. Neptune Pass represents the largest new distributary to form on the Mississippi River in nearly a century. The last comparable event was the formation of the Wax Lake Delta, which emerged about 150 miles to the west during the 1970s. The water carved through sediment and soil with remarkable efficiency, widening the channel by an order of magnitude in less than 2 years. As the channel grew wider and deeper, it could accommodate even more water flow, creating a self-reinforcing cycle where more flow meant more erosive power. Scientists along the Gulf Coast haven't witnessed anything like Neptune Pass's rapid development in over half a century, making this a once-in-a-generation opportunity to study river mouth formation in real time. How rivers naturally build land. To truly appreciate what Neptune Pass represents, we need to understand the fundamental geological principles of how rivers build deltas and create new land. For millions of years, large rivers like the Mississippi have carried enormous quantities of sediment from the continental interior to coastal areas. This sediment, made up of silt, sand, clay, and organic matter, is picked up along the river's journey as it erodes banks, cuts through soft rock formations, and collects material from countless tributaries feeding into the main channel. When a river reaches the coast and meets the ocean, something fascinating happens. The water slows down as it spreads out into the broader Gulf waters. As the current decreases, the river can no longer carry all the sediment it's been transporting. The heavier particles settle out first, followed by progressively finer materials. Over time, these sediment deposits accumulate, building up underwater features that eventually rise above the waterline to form new land. This is how river deltas are born and how they continue to grow over geological timescales. The Mississippi River system has been practicing this land-building process for millions of years. Before modern engineering intervened, the river would naturally shift its course, find new outlets, create distributary channels, and deposit sediment across a wide coastal plain. These natural processes created the vast Louisiana Delta that exists today, a landscape that wouldn't exist at all without Mississippi's sediment delivery system. In fact, if not for the sediment carried by the Mississippi River over thousands of years, most of Louisiana and a substantial portion of Mississippi wouldn't exist above water. Prior to 1900, the Mississippi River transported an estimated 400 million metric tons of sediment per year from the interior United States to coastal Louisiana and the Gulf of Mexico. This massive sediment load continuously nourished the delta, allowing new land to form faster than natural subsidence and erosion could remove it. The river would overflow its banks during floods, spreading nutrient-rich sediment across floodplains. It would occasionally jump to new courses, abandoning old channels and creating new distributary systems that reached different parts of the delta. Neptune Pass is giving scientists a front-row seat to watch these ancient geological processes in action. As water diverts through Neptune Pass, it carries sediment into Quarantine Bay and Bay de Ness. When the water slows in these bays, the sediment drops out of suspension and begins accumulating on the bay floor. Research teams led by coastal geologist Alex Coker have documented this land-building process through detailed surveys and sediment core samples. Between 2019 and 2022, approximately 6 million cubic yards of sediment were diverted from the Mississippi through Neptune Pass and deposited into these bays. Some of this new land is already visible above the waterline during periods of low water, with aquatic vegetation taking root, a sign that the delta building process is well underway. The engineering that changed everything. The story of Neptune Pass cannot be told without understanding how dramatically humans have altered the Mississippi River over the past century and a half. When settlers began moving into the Mississippi River Valley in large numbers during the 1800s, they faced a fundamental problem with seasonal floods destroying crops, homes, and infrastructure. The levee-building effort began in earnest during the mid-1800s and expanded dramatically throughout the 20th century, creating massive earthen walls designed to keep floodwaters confined to the main channel. While these levees accomplished their primary goal of protecting human settlements and agricultural lands, they fundamentally changed the river's behavior in ways engineers didn't fully anticipate. By constraining the river within levees, engineers prevented the natural process of sediment distribution across the floodplain, and when levees blocked this natural process, the delta stopped receiving the sediment it needed to maintain itself. Additional human modifications compounded the problem dramatically. Engineers constructed numerous dams on the Mississippi and its major tributaries, particularly the Missouri and Ohio rivers, which trap sediment in their reservoirs and prevent it from reaching the Gulf. The Army Corps of Engineers also implemented programs to straighten the river's course by cutting across meandering bends, reducing the river's length, and increasing its current velocity. Bank revetments prevented natural erosion that would normally contribute sediment to the system, while soil conservation programs upstream reduced the amount of sediment entering the river. All these interventions worked together to choke off the delta's natural sediment supply. The cumulative impact of all these changes has been staggering. During the last 2 decades, the Mississippi River has transported only about 145 million metric tons of sediment per year, less than half the historical rate of 400 million metric tons. Meanwhile, Louisiana's coastal wetlands have suffered catastrophic land loss, with more than 2,000 square miles of Louisiana's delta already sunk below the waterline and eroded into the Gulf. Bretong Sound, where Neptune Pass is building new land, has lost approximately 42% of its wetlands over the past century due to this combination of reduced sediment input, subsidence, sea level rise, storm damage, and canal construction. A window into the river's natural behavior. Neptune Pass offers scientists something extraordinarily valuable: observational data on how a large river distributary develops naturally in real time. Throughout most of human history, rivers around the world freely formed and abandoned distributary channels as part of their natural behavior, but the development of modern surveying technology coincided with an era when most major rivers became heavily engineered and controlled. The Mississippi River has historically experienced numerous changes to its main course over geological time, shifting between various distributary channels as old routes became clogged with sediment or new, more efficient paths opened up. However, modern flood control infrastructure has essentially frozen the river in place, preventing the natural channel switching that characterized the river's behavior throughout its geological history, which makes Neptune Pass incredibly valuable for scientific study. Research teams are now documenting every aspect of Neptune Pass's development with modern technology. They conduct aerial surveys from small aircraft and analyze satellite imagery to track changes in the channel's width and path, take boats into Quarantine Bay to collect sediment cores that reveal the composition and accumulation rate of new deposits, and measure water discharge rates at different points along the channel during various stages of Mississippi River flow. Scientists can now measure exactly how much water flows through a newly formed distributary, track the sediment deposition rates in the receiving basin, monitor the development of the delta formation, and observe how aquatic ecosystems respond to the influx of fresh water and sediment. Please like and subscribe channel.